Good day. Today we are learning about spectroscopy. In spectroscopy, you are getting knowledge on what is spectroscopy, what are the principles involved in UV and visible spectroscopy, and what are the different types of electronic transition. Let us see what is spectroscopy. Spectroscopy is the measurement and interpretation of electromagnetic radiation absorbed or emitted when the molecules or atoms or ions of a sample move from ground state to the excited state or from excited state to ground state. At ground state, the energy of a molecule is the sum of total of rotational, vibrational and electronic energies. Hence, spectroscopy measures the changes in rotational, vibrational and electronic energies. Electromagnetic radiation is made up of discrete particles called photons. A photon consists of oscillating electric field and oscillating magnetic field which are perpendicular to each other. Hence, electromagnetic radiation has got both wave characteristic as well as particle characteristics. You can see in the diagram electric field and magnetic field which are perpendicular to each other. There are different types of electromagnetic radiations like visible radiation, UV radiation, IR radiation, microwaves, radio waves, X-rays, gamma rays or cosmic rays. These radiations have different wavelength or frequency or energy. Let us see what is the principle involved in visible spectroscopy. Visible spectroscopy is also called as colorimetry. What is colorimetry? Colorimetry is the study of absorption of visible radiation whose wavelength ranges from 400 to 800 nanometers. Any colored substances absorb radiation in this wavelength region. Colored substances absorb light of different wavelengths in different manner, hence we get an absorption curve. Absorption curve you can observe in the diagram. In the absorption curve, x-axis is wavelength and y-axis is absorbance. In this absorption curve, the wavelength at which maximum absorption of radiation takes place is called as lambda max. This lambda max is characteristic or unique for every colored substance and this is qualitative aspect and useful in identifying the substance. Lambda max usually not affected by concentration of a substance. You can see here in the diagram how it is not affected by the concentration of a substance. Here, the absorbance of solution increases with increasing the concentration of a substance, but the lambda max doesn't change when concentration changes. This is called as absorption curve. And coming to the calibration curve, when a graph of concentration versus absorbance is plotted, a calibration curve or standard curve is obtained. This calibration curve is useful in determining the concentration or amount of a drug substance in the given sample solution or a formulation by extrapolation or interpolation and calculation is obtained. Let us see the principle involved in UV spectroscopy. What is UV spectroscopy? UV spectroscopy is the study of absorption of UV radiation which ranges from 200 to 400 nanometers. In this region, colorless compounds absorbs UV radiation. In both UV as well as visible spectroscopy, only valence electrons absorbs the energy. Let us see what is principle involved in UV spectroscopy. In UV spectroscopy, any molecule has either n, pi or sigma electrons or combination of these electrons. These bonding and non-bonding electrons absorb the characteristic UV radiation and undergoes transition from ground state to excited state. By the characteristic absorption peaks, the nature of electrons present and then molecular structure can be elucidated. Let us see what are the different types of electrons present in any molecule. Types of electrons present in any molecule can be classified as sigma electrons, pi electrons, n electrons. Sigma electrons. These are the ones present in saturated compounds. Such electrons do not absorb near UV but absorb vacuum UV radiation, that is less than 200 nanometers. Pi electrons. These electrons are present in unsaturated compounds. Example, double bonds or triple bonds. N electrons. These are non-bonded electrons which are not involved in any bonding. Example, lone pair of electrons. Let us see what are the electronic transitions and excitation process in UV spectroscopy. The following electronic transitions are possible in UV spectroscopy. Pi to antibonding pi transition, N to antibonding pi transition, sigma to antibonding sigma transition, N to antibonding sigma transition. You can observe the electronic energy states: ground state and excited state. What is N to antibonding pi transition? In this transition, excitation of electrons from non-bonding to anti-bonding excited state. And this electronic transition requires lowest energy. The peaks due to this transition is called as R bands. This type of peak can be seen in compounds where N electrons present in double bond or triple bond. The presence of N2 antibonding pi transition can be identified by comparing the UV spectrum of a substance with the spectrum recorded in acid solution of the same substance. In an acid solution, the band disappears if N2 antibonding pi transition has been present. Examples of N2 antibonding pi transition are aldehydes or ketones, nitro compounds. Pi to antibonding pi transition. Excitation of electron from pi bonding to anti-bonding pi excited state. The energy requirement of this transition is between N2 antibonding sigma and N2 antibonding pi. Extended conjugation and alkyl substituents shifts the lambda max towards longer wavelength. Extended conjugation means addition of more bonds, that is double bond or triple bonds. And also, trans isomer of olefin absorbs at longer with more intensity than cis isomer. Longer wavelength is also called as bathochromic shift and with more intensity, that is hyperchromic effect. Bands due to this transition are B bands, E bands, K bands. B bands are due to aromatic and heteroaromatic compounds. E bands are due to aromatic compounds. K bands are due to conjugated compounds. N2 antibonding sigma transition. In this transition, excitation of electron from non-bonding to anti-bonding sigma excited state. It requires lesser energy when compared to sigma to anti-bonding sigma transition. Normally, the peaks due to this transition occurs from 180 to 250 nanometers. These peaks appear at lower end of the UV spectrum called end absorption. This transition occurs in saturated compounds with heteroatoms like sulfur, oxygen, nitrogen or halogens. Examples of these compounds are methylene chloride, water, methanol, ethanol, ether, trimethylamine, chloroform, carbon tetrachloride. Sigma to antibonding sigma transition. In this transition, excitation of electron from sigma bonding to anti-bonding sigma excited state requires highest energy for transition. These peaks do not appear in the UV region but occur in vacuum UV or for UV region, that is 125 to 135 nanometers. This type of transition occur in saturated compounds, especially hydrocarbons. Since UV spectrophotometers are operated above 200 nanometers, saturated hydrocarbons can be used as non-polar solvents as it doesn't give solvent peaks. Example of this transition are methane, ethane, propane and cyclopropane. These are the different types of electronic transitions in UV spectroscopy, and the energy required for excitation for these different electronic transitions are N2 antibonding pi requires lesser energy when compared to pi to antibonding pi transition than N2 antibonding sigma transition than sigma to antibonding sigma transition. Hence, sigma to antibonding sigma transition requires highest energy for transition whereas N2 antibonding pi transition requires lowest energy. Thank you.